Hello and welcome to Math 1111 video on basic functions and characteristics of functions by Andrea Hendricks. I hope this finds you doing well. We have a lot of objectives to cover, but I would say that most of these are going to be visual exercises, not too much of difficult algebraic skills. We're going to look at some graphs of basic functions, which are the identity function, the squaring function, the cubing function, the square root function, the cube root function, and the absolute value function. These are graphs that you should know really pretty much by heart without having to type into the calculator and get the graphs. And I think you'll get a feeling for that as we go through this. You should also be able to determine if a function is continuous and the intervals of continuity. We should be able to determine intervals where a function is increasing, decreasing, or constant, and determine if a graph is symmetric with respect to the x-axis, y-axis, or origin, and lastly, determine if a function is even or odd. I know it sounds like a lot, but those last two objectives actually are really the same. Even and odd are defined in terms of something that you'll find in Objective 4. So let's look at Objective 1a, that is to be able to graph the identity function. What is the identity function? It is a function f of x is equal to x. Now remember, what does f of x mean? F of x is y. So this is a function where the input is equal to the output, right? Like if I had a chart and I put in -2, -1, 0, 1, and 2 into this function, what am I going to get out of it? Well, if I put in -2, I'm going to get out of it -2. If I put in -1, I'll get out -1, 0, 1, and 2, respectively. Right, because my function rule is saying that my input is equal to the value of the output. Or vice versa, if you want to say the output is equal to what you input into the function. So whenever we graph that, hopefully you recognize that as one of our linear functions, right? We look at y is equal to mx plus b, and we have the graph of y is equal to 1x, or just y is equal to x. Our slope is the coefficient of x, which is 1. The value of b, which is our constant term, is 0, and that is our intercept, right, our y-intercept. So whenever we graph this function, we get a straight line with a slope of 1 through the origin. Now again, if you had graph paper and pencil, you could see this really precisely. Done it as good as I can here, but that is the identity function. Okay, so it is a line through the origin with slope 1. What is the domain and range? Those concepts you're not going to really ever get away from. I'll probably ask you that on almost every question that you have on a test. The domain of this function is what do our values of x take on, what can we put in to get something that makes sense, or how does the graph go from the left direction to the right direction, and that is from -infinity to infinity. And the range is our y values, right, from bottom up, and that's from -infinity to infinity as well. The next of our basic functions is the squaring function. I'm going to use FCN to abbreviate function. The squaring function is if I put in a value, my output value is going to be the square of that. So if I put in -2 and square it, I get 4. If I square -1, I get 1. If I square 0, 0, squaring 1, 1, and squaring 2, 4. Now I could use any value of x. I'm just using nice, pretty numbers. And then whenever we graph this, we're going to get -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. This is our basic parabola, a quadratic equation or quadratic function. Quadratic meaning the power of 2. Always has a shape called a parabola. Now what about the domain and range of this? Domain, it extends indefinitely from the left and the right direction. It's negative infinity to infinity. The range is the bottom up. Well, our bottommost value is this 0, 0. So my range goes from 0 and then on up to infinity. You could input all of these on a calculator, and I'll talk about that in the calculator video. Here we're just trying to practice by hand. F of x equals x cubed. We would cube our value of x that we put in. Just be careful for signs. When you cube a negative 2, you get a negative 8. When you cube negative 1, you get negative 1. Cubing 0 gives you 0. Cubing 1 is 1, and 2 cubed is 8. So looking at the graph of this, negative 2, negative 8, negative 1, negative 1, 0, 0, 1, 1, and 2, 8. So this kind of looks like a snake, right, as we curve around there. The domain and range of this function are, what do you think? In the left to right direction, it goes on indefinitely, so that would be from negative infinity to infinity. The range, also from bottom up, extends indefinitely from negative infinity to infinity. A few more functions to look at. The square root function. When I input into the square root function, I have to be very careful, right? I cannot take the square root of a negative number, and so I can only start with values of 0 and positive. And I'm going to choose nice, pretty numbers because I know the square roots of 0, 1, 4, and 9. You could certainly put in like 2 and 3 and 5. You would just get an irrational number, and that's fine. The square root of 0 is 0. The square root of 1 is 1. The square root of 4 is 2. And the square root of 9 is 3. So if I graphed that, again, hopefully you would have graph paper. 0, 0, 1, 1, 4, 2, and 9, 3. Okay. So this one is kind of like a half parabola. And if you look in your textbook, you can see a more official picture of that, or on your calculator. The domain is left to right. Our leftmost point is 0, 0. So it is from 0 to infinity. Now the range is from bottom up. Now the y value at that bottommost point is 0, so it's from 0 to infinity. Believe it or not, this does go on up to infinity. If you put in the square root of 1 billion, you're going to get a really large number. Okay. What about the cube root function? Well, the cube root function is a little bit different than the square root function. I don't have any restrictions on what I can put in because the cube root of a negative is a negative value. Now I'm going to choose numbers that are nice for me to work with by my head because I know the cube root of negative 8 is negative 2. I know the cube root of negative 1 is negative 1. The cube root of 0 is 0. Cube root of 1 is 1. The cube root of 8 is 2. The cube root is actually defined for any number, so you could put that into the calculator if you want to get a decimal value. So whenever you graph this, just put some labeling here. So if I have negative 8, negative 2, negative 1, negative 1, 0, 0, 1, 1, and then 8, 2. So this graph is going to come through here. Okay. And our last basic function is absolute value. So to graph absolute value by hand, you can put in some negative values, 0 and a positive value, or 2. Absolute value of negative 2 is 2, right? Absolute value just means distance from 0. So all of the absolute values are going to be positive. And whenever we graph that, we would get negative 2, 2, negative 1, 1, 0, 0, 1, 1, and 2, 2. So this is a V-shaped graph. And the domain is all reals because it goes indefinitely from left to right. What about the range? We read from bottom up. Yet that bottommost point is 0, 0, so the y value of that is 0, and it extends indefinitely up to infinity. So absolute value graphs are going to be V-shaped, at least when you have a linear expression inside. Okay? So let's look at the next objective. A function f of x is continuous, so a new term here, on an interval of the domain if the graph can be sketched without lifting your pencil on this portion of the graph. Well, if you look at all of the ones we've done in those previous problems, I could put my pencil down and not lift it to draw a straight line, right? So that identity function is continuous. Is the squaring function continuous? Yes, I can draw the graph without lifting my pencil. Same thing with the x cubed or the cubing function. The square root function I can draw without lifting my pencil. The cube root function I can draw without lifting my pencil. The absolute value function I can draw without lifting my pencil. So all of the previous basic functions that we just talked about are continuous on their entire domain. So what would not be a continuous graph? If I have a graph, which we're going to talk about in a later section, that looks like this. This is an example of what we'll see later on as a rational function. I could not draw that without picking up my pencil, right? And so this has a point, we say, of discontinuity that is at this point 0 where my two pieces were separated. So at x equals 0, I have this point of discontinuity, and you're not even going to need to worry about all of that right now. You would need to be able to say, though, where is it continuous? Well, it has two pieces where it's continuous. It is continuous at, if I can spell continuous, on negative infinity to 0, but with a parentheses now, and then from 0 to infinity, right? From in the left direction up to 0 is continuous because I did that one whole piece without lifting my pencil. And then I moved over and started from 0 to infinity to do the next piece. Another type of function that's not continuous, you'll see maybe an example where you have oops, let me make that open circle here. Something like that where you have a gap in the graph. So it's continuous on this piece and on this piece, but not over the entire domain. So let's say maybe this is a point x value of 1. So you would say it's continuous at negative infinity to 1, right? And then from 1 to infinity. You can also see graphs that have holes in them, so anything like that is not a continuous graph. Now, our next objective is a function is increasing, well, let me back up. It's to be able to determine from a graph where the function is increasing decreasing, or constant. Now, increasing, decreasing, or constant are what's going on with the y values. But the interval we answer with are the x values. Okay? So we're really saying for what values of x are the y values increasing, decreasing, or constant. Now the mathematical way that we define this is we say a function is increasing on an interval if the y value at x1, that is f of x1, is less than the y value at x2 when x1 is less than x2. Now, you're thinking, what in the world does that mean? Well, let's say here's x1 and here's x2. So here's our point. Okay. Well, the y1 value is here and the y2 value is here. So when x1 is less than x2, our value of y1 is less than y2, or f of x1 is less than f of x2. And that would happen when what happens? If you connect those, the function has to be rising, or we say it's increasing from left to right. So you always read these graphs from left to right. Now a function is decreasing on an interval if f of x1 is greater than f of x2 for x1 less than x2. So what does that mean? Here's my x1, here's my x2. Here's my y1 now and my y2, because it said that y1, right, f of x1, we'll call it y1, is greater than f of x sub 2, we'll call that y sub 2. So that means that as I go from left to right, the function is falling or decreasing. Now, a function is constant on an interval if f of x sub 1 is equal to f of x sub 2 for every x1 and x2. So here is my x sub 1, my x sub 2. Well, this would have to say that the y1 and y2 are equal. Okay. Oops, I took that off there, didn't it? In other words, you have a constant or a horizontal line connecting the pieces where your function is constant. Now, I have an interesting application to kind of show you that maybe hits home to understand why we need that. If you look in the world around you today, I mean, we're overwhelmed with numbers, right? Numbers are everywhere, and it's very helpful to be able to get a grasp of what do those numbers tell us. And truly the only way to do that is to visualize it, to get a picture. We can do that in one of two ways, either like a bar graph or a line graph. And from that you can really examine more closely what's happening with that data that you've been given. I mean, beyond the fact that increasing, decreasing, constant functions are so important when we get into the topic of calculus. So if you've got to go on in your math, you're going to see this from a mathematical perspective dealing with functions, but realistically in real life it's going on around us every day as well. And so if I'm looking at this, I went to the internet and I Googled cells about Macs and stuff. I know we've kind of been talking about if you have a PC or a Mac, and these are the cells in quarters after 2005, so the first quarter after 2005, that is the first quarter in 2006, Mac cells were 1.11 million, and up to 2.32 million, basically 2 years after 2005. And here's my source where I found this. But what I did is I put this in an Excel spreadsheet and I plotted the data just so we can kind of get a feel for it. Notice that the function is increasing except for here, right? Between the third and fourth quarters it was constant, and then it decreased slightly, and then it's increasing again. So I think if you have a real life context to think about, the increasing and decreasing will make more sense to you. So where would we say it's increasing? So this one we would say is increasing on the interval from what, 1 to 3. And also where from 5 to 8. Where is it decreasing? It's decreasing on the interval from 4 to 5. And where is it constant? It's on the interval from 3 to 4. So you understand that I knew if it was increasing, decreasing, or constant because of what was happening to the y values. But my answer had to be the x values. Here's another interesting one, iPod sales. Now you can see a spike in sales when Christmas time is around. But here's a chart that's looking at that. So notice what's happening. From the first quarter to the second quarter, there was a slight decrease, and then there was an increase, a sharp decrease, and then it increased again. So this one wasn't constant anywhere, but we can talk about where it's increasing and decreasing. So where was it increasing? It increased from the interval from 2 to 4, right? Between 2 and 4 it was increasing, between here. And then it also was increasing from, I'm going to have to look at my numbers here a little bit better, from 6 to 8. I'll put the brackets there because the points are included on my graph. And then where did it decrease? It was decreasing on the interval from 4 to 6. Okay. Now we're going to see this with algebraic functions, but it's the same principle that you're doing. You're reading the graph, looking visually to see if it's rising or falling, or if it's not moving, that if it's horizontal, and then answering with the values of x. Now, the last two objectives are very closely related. It deals with the concept called symmetry. If you think about symmetry, you know, like even if you're decorating, right? When you think of something that's symmetric, something that's balanced, something that looks the same on both sides, well, that's really what we're talking about mathematically. We say a function f of x is symmetric with respect to the y-axis if f of negative x is equal to f of x. Again, what are you thinking about with f of negative x and f of x? What do those mean? F of negative x means the y value at the opposite of x, right? And f of x means the y value for value of x. In other words, this is saying that negative x and x have the same y value. This is saying the output value when x is its opposite is the same as the output value for the value of x. So if the y values are the same for opposite x values, we're saying that this one is balanced with respect to the y-axis. In other words, the images on the left side and the right side of the y-axis are the same. Okay? So what would I think about with something like that? Do you remember that squaring function we talked about? Or that absolute value function we talked about? On the left side and right side, those images are identical. Those would be symmetric with respect to the y-axis. Symmetric with respect to the origin means f of negative x is equal to the opposite of f of x. F of negative x is equal to the opposite of f of x. So this is saying the output value for negative x is the opposite of what it was for x. In other words, negative x and x have opposite y values. So xy would be a point on the graph, but also negative x, negative y would be a point on the graph of that function. Well, let me go back up here if I can for a minute. Hope you don't mind me scrolling. There were several places where this happened. Do you remember this cubing function? Negative 2, negative 8, 2, 8, right? Opposite values of x had opposite values for y. Negative 1, negative 1, 1, 1. Opposite values for x had opposite y values. That's what it means to be symmetric with respect to the origin. Now, what did the graph look like? Well, the graph looked like basically this. A way to think about it is the side, left side and right side of the y-axis are opposite of each other. Okay, they're flipped images of each other. That's what it would mean to be symmetric with respect to the origin. There's a lot of different ways to kind of say this, and I'll say those differently in different ways on different videos probably, and I'll hopefully relate them all to you together. But symmetric with respect to the origin means images on the left side and right side of the y-axis, or of the origin even. On the left side and right side of the origin are flipped. So an example of that was the cubing function, or the cube root function. Symmetric with respect to the x-axis. Now, for a function to be symmetric with respect to the x-axis, I should not even say that because it's not a function. Because what that would mean is that if we look on each side of the x-axis, you have to see a mirror image. So the only way for that to happen is if it doesn't pass the vertical line test. So these, or this case, would not be a function. It would be a relation, but not a function. So in this case, we would say the relation is symmetric with respect to the x-axis. But we would say here that the images above and below the x-axis are the same. Okay? In other words, they're mirror images of each other. If you flipped this piece over on the x-axis, in other words, if you could fold the graph along the x-axis, you would see a mirror image. You would see the same picture. So this would be an example of something like that. I really hate for this to be so messy. I hope you can follow along with that. Now, determine symmetry. You should be able to determine it analytically, graphically, and from a table. Analytically, you would actually have to plug in f of negative x and compare the result to the original function. So if the original function results we have symmetry with respect to the y-axis. If the opposite of the original function results, we have symmetry with respect to the origin. If neither the same nor the opposite happen, then it's neither of those symmetries. Okay. Now, graphically, you're going to have to look at the images on the left side and right side of the y-axis to determine if it's the same image or if it's a flipped image. So for it to be symmetry with respect to the y-axis, the images have to be identical on either side of the y-axis. For it to be symmetric with respect to the origin, the images on either side of the y-axis have to be flipped. Now in a table, you're going to kind of do what I talked about earlier with that cubing function. You're going to have to look at the y values for opposite x values. And you're going to determine, are they the same or opposite? Okay. If they're the same, you've got symmetric with respect to the y-axis. If they're opposite, you have symmetric with respect to the origin. And if they're neither one of those. Okay? I have some examples worked in your exercises, so don't panic. You're going to see plenty of these worked. Even in odd functions, lucky for you, that's just a new term for something we've just discussed. An even function is a function that's defined when f of negative x is equal to f of x. Well, we just saw that. That means that it is symmetric with respect to the y-axis. An odd function, f of negative x is equal to the opposite of f of x, which is symmetric with respect to the origin. Okay? So, watch the homework video, watch the calculator video, because I'm going to show you how you can determine these types of symmetries and whether or not a function is even or odd using the methods that we've kind of described here. So a lot of material in this, but I think it's going to be really visual for you. Just a little bit of algebraic skills that you have to do by plugging in f of negative x, and I've illustrated that in the next video. So thank you and have a great day.